What if I told you there's a welding process so powerful it can create welds up to 10 times faster than traditional methods, yet it's completely hidden from view? Welcome to the world of submerged arc welding, the industrial giant of the welding world, and today we are diving deep into one of the most fascinating and efficient welding processes ever invented. By the end of this video, you'll understand why SAW is the backbone of industries building everything from ships to pipelines. So what exactly is submerged arc welding? SAW is an arc welding process where the arc is struck beneath a blanket of granular flux. Let me break this down. Unlike stick welding or MIG welding where you can see the bright arc, in SAW, the welding arc is completely hidden under a layer of powdered flux material. Here's what happens. A continuous solid, a tubular electrode wire is fed automatically into the weld joint. At the same time, granular flux is deposited over the welding area from a hopper. When the electrode makes contact with the workpiece, an electric arc forms, but you can't see it because it's buried under 1 to 2 inches of flux. This flux melts from the heat, creating a protective molten pool that shields the weld from atmospheric contamination. The beauty of this process? It's almost entirely automatic, incredibly fast, and produces welds of exceptional quality. The story of SAW begins in the early 1930s. The process was independently developed in the United States and the Soviet Union almost simultaneously. In America, the National Tube Company worked with the Lind Air Products Company to develop the process, which was initially called the Union Melt process. Why was it invented? During the industrial boom, manufacturers needed a way to weld thick steel plates faster and more reliably. Traditional welding methods were too slow for mass production. SAW solved this problem brilliantly. By the 1940s, during World War II, SAW became critical for building ships, tanks, and other heavy equipment quickly. The Liberty ships program used SAW extensively, helping produce vessels at unprecedented speeds. Today, SAW technology has evolved with computerized controls, multiple wire systems, and sophisticated flux formulations, but the basic principle remains unchanged: hide the arc under flux for better, faster welds. Let's talk equipment. A SAW system consists of several key components, and understanding each one is crucial. First, the welding head. This is the heart of the system. It houses the electrode wire, contact tip, and flux delivery system. Most modern systems use fully automatic welding heads that travel along a track or gantry. Second, the electrode wire. SAW typically uses solid wire electrodes ranging from 1.6 mm to 6 mm in diameter. For special applications, tubular or metal cord wires can be used. The wire is fed continuously from large spools, some weighing hundreds of pounds. Third, the flux delivery system. This includes a hopper that holds the granular flux and a mechanism to deposit it evenly ahead of and around the electrode. The flux recovery system is equally important. It vacuums up the unfused flux for reuse. Fourth, the power source. SAW requires hefty power, typically DC or AC power sources ranging from 400 to 1500 amps or more. Some systems use multiple power sources for multi-wire welding. Fifth, the travel mechanism. This could be a motorized carriage, tractor, or boom that moves the welding head along the joint at controlled speeds. Finally, the control system. Modern SAW systems feature sophisticated controls for wire feed speed, travel speed, voltage, amperage, and flux delivery rate. Many are now computer controlled with programmable settings. Now let's talk about flux, the secret ingredient that makes SAW special. This isn't just any powder, it's a carefully engineered material with multiple critical functions. Protection. The flux creates a protective atmosphere around the weld, preventing oxygen and nitrogen from contaminating the molten metal. This eliminates porosity and ensures strong, clean welds. Arc stability. The flux helps stabilize the welding arc, making the process smoother and more consistent. Weld shape control. The flux influences the shape and penetration of the weld bead. Different flux formulations create different weld profiles. Slag formation. As the flux melts, it forms a slag layer that covers the weld, slowing the cooling rate and preventing rapid temperature changes that could cause cracking. Alloy additions. Some fluxes are formulated to add alloying elements to the weld, improving its mechanical properties. There are two main categories of flux. Fused fluxes are made by melting raw materials together and then crushing the solidified product into granules. They're glass-like and moisture-resistant. Bonded fluxes are made by mixing and binding powdered ingredients together. They're more versatile but require careful drying before use. Fun fact: the unused flux can be recycled up to 20 times if properly managed, making SAW economically and environmentally attractive. Let's walk through the actual welding process from start to finish. Step 1. Preparation. The workpiece edges are prepared, cleaned, and positioned. For thick materials, bevels might be cut to ensure proper penetration. The pieces are clamped or tack welded to prevent movement. Step 2. Setup. The welding head is positioned at the starting point. Parameters are set: wire feed speed typically 70-50 inches, travel speed 10-60 inches, and current 400,000 amps depending on the application. Step 3. Flux deposition. Before welding starts, a layer of flux is deposited over the joint path, creating a mound about 1 to 2 inches deep. Step 4. Arc initiation. The electrode wire is fed down to touch the workpiece, initiating the arc. Within seconds, the arc is completely submerged under the flux blanket. Step 5. Welding. As the welding head travels, the arc melts the electrode wire, base metal, and flux. The molten weld pool forms beneath the flux, completely hidden from view. The travel mechanism maintains steady forward motion. Step 6. Cooling and solidification. Behind the welding head, the weld metal solidifies, covered by a protective slag layer. This slag is brittle and easily chips off once cooled. Step 7. Flux recovery. A vacuum system following behind the welding head collects the unfused flux for reuse. Step 8. Slag removal. After the weld cools, the slag is chipped or ground off, revealing a smooth, clean weld bead underneath. What's remarkable is that steps 4 through 7 happen simultaneously and continuously, making SAW incredibly productive. SAW isn't just one technique, there are several variations designed for different applications. Single wire SAW. This is the most common setup, using one electrode wire. It's perfect for general purpose welding and provides excellent control. Twin wire SAW uses 2 electrodes in tandem, typically sharing the same weld pool. This nearly doubles the deposition rate without needing massive increases in power. Tandem arc SAW, similar to twin wire, but with 2 separate power sources. This provides even more control and can achieve deposition rates up to 100 pounds. Multi-wire SAW. Some advanced systems use 3, 4, or even more wires simultaneously. This is used for extremely thick materials or when production speed is critical. Narrow gap SAW. For welding very thick plates, the groove is made narrow. An specially designed flux and electrode system welds in the confined space, saving time and filler metal. Strip cladding SAW. Instead of wire, a flat metal strip is used as the electrode. This is perfect for applying corrosion-resistant cladding to large surfaces quickly. The choice depends on material thickness, production requirements, and weld quality specifications. Why do industries love SAW? Let me count the ways. Incredible speed. SAW is typically 5 to 10 times faster than manual welding methods. For thick materials, it's unmatched in productivity. Superior quality. The flux protection produces welds with excellent mechanical properties, minimal porosity, and consistent quality. X-ray testing often shows near-perfect results. Deep penetration. SAW can penetrate thick materials in a single pass, reducing the need for multiple weld passes. High deposition rate. The process can deposit 20 to 100 pounds of weld metal, depending on the setup. Minimal operator skill required. Once programmed, the process is automatic, reducing dependence on highly skilled welders for production work. Clean operation. There's no visible arc, minimal spatter, and no fumes in the operator's breathing zone. It's one of the safest welding processes. Economical. Despite high equipment costs, the fast welding speeds and minimal waste make SAW very cost-effective for high-volume production. Excellent finish. SAW produces smooth, uniform weld beads that often require minimal finishing work. These advantages make SAW the go-to choice for heavy fabrication industries worldwide. As amazing as SAW is, it's not perfect for every situation. Let's be honest about the limitations. Position restriction. SAW works best in the flat position. The flux must stay in place, so welding vertical or overhead joints is impractical with standard SAW. Some specialized systems can handle horizontal fillet welds, but that's about it. Joint accessibility. The welding head is relatively large and bulky. You need good access to the joint, which rules out tight spaces or complex geometries. Setup time. While the actual welding is fast, setting up the equipment, programming parameters, and positioning workpieces takes time. This makes saw less economical for small production runs or one-off jobs. High initial investment. The equipment is expensive. A complete saw system can cost from $50,000 to over $500,000, depending on sophistication. Limited to thick materials. While saw can weld thin materials, it's overkill for anything under 3 by 16 inch thick. Other processes are more suitable for thin gauge work. Flux handling. Managing flux storing, drying, recycling, and preventing contamination adds complexity to operations. Limited portability. Saw systems are generally stationary or semi-portable. You can't carry a saw setup to a remote job site easily. Understanding these limitations helps you choose the right welding process for your specific needs. Where do you find saw in action? Pretty much anywhere heavy metal fabrication happens. Shipbuilding. This is SAW's original home. Hull panels, decks, and structural members are all welded using saw. A single large ship might contain miles of saw welds. Pressure vessel manufacturing, storage tanks, boilers, and pressure vessels for chemical plants and refineries rely on saw for their critical seam welds. The high quality is essential for safety. Pipeline construction. Large diameter pipes for oil, gas, and water transmission are manufactured using saw. Both longitudinal and circumferential seams are commonly saw welded. Structural steel fabrication, bridges, buildings, and offshore platforms use massive saw welded H-beams, I-beams, and box sections. Heavy equipment manufacturing, construction equipment, mining trucks, and agricultural machinery incorporate saw welded components for strength and durability. Railroad industry, rail car manufacturing, and track welding utilize saw for high productivity joining of thick steel components. Wind turbine towers, those massive tubular towers supporting wind turbines. Many are assembled using saw. Automotive and rail rolling stock, train car bodies, and heavy truck frames are often saw welded in automated production lines. Basically, if it's big, thick, and needs to be welded in quantity, saw is probably involved. While saw is one of the safer welding processes, safety protocols are still critical. Eye protection. Even though the arc is hidden, molten metal and hot slag present hazards. Safety glasses with side shields are minimum, full face shields are recommended when removing slag. Protective clothing. Flame-resistant clothing, leather gloves, and steel-toed boots protect against burns from hot metal and slag. Ventilation. Although fumes are less than other processes, proper ventilation is still necessary, especially in confined spaces. The flux decomposition can release gases that shouldn't be breathed. Electrical safety. Saw uses high amperage power. Proper grounding, cable inspection, and lockout, TAGU procedures prevent electrical accidents. Machine guarding. Moving parts on automated systems must be properly guarded. Emergency stop buttons should be easily accessible. Flux handling. Flux can be a respiratory irritant. Use masks when handling dry flux, and store it properly to prevent moisture contamination. Hot work permits. In many facilities, saw operations require hot work permits and fire watch procedures. Training. Operators must be trained not just in welding, but in equipment maintenance, troubleshooting, and emergency procedures. Remember, no production schedule is worth compromising safety. Where is saw technology heading? The future looks exciting. Artificial intelligence and machine learning. Modern systems are incorporating AI to optimize parameters in real time, predicting and preventing defects before they occur. Advanced sensing systems, laser and camera-based seam tracking systems guide the welding head with millimeter precision, eliminating defects from joint misalignment. Hybrid processes. Researchers are combining saw with laser welding or arc augmentation for even higher speeds and deeper penetration. Smart flux development. New flux formulations are being developed with enhanced properties, including self-shielding capabilities and improved metallurgical performance. Remote monitoring. IoT connectivity allows real-time monitoring of saw operations from anywhere in the world, enabling predictive maintenance and quality assurance. Sustainability focus. Efforts are underway to develop more environmentally friendly fluxes and improve energy efficiency of saw systems. The fundamental principle of saw arc under flux will remain, but the execution is becoming increasingly sophisticated and automated. And there you have it, a complete dive into submerged arc welding. From its invention in the 1930s to today's AI-enhanced systems, saw has been and continues to be the workhorse of heavy industry. We've covered what saw is, how it works, the equipment involved, its advantages and limitations, and where it's used. Whether you're a welding student, an engineer, or just someone fascinated by how things are made, understanding saw gives you insight into one of the most important manufacturing processes in modern industry. If you found this video helpful, please hit that like button and subscribe for more in-depth technical content. Got questions about saw or want to see other welding processes explained? Drop a comment below. I read them all, and your feedback shapes future content. Thanks for watching, and remember, behind every massive structure, there's probably miles of submerged arc welds holding it all together. Until next time, keep learning and stay curious.